Hey everybody, my name is Calvin, and today we'll be talking about the stack data structure in Python. Every programmer eventually runs into the concept of a stack. It shows up in web browsers, text editors, algorithms, and even inside Python itself. Despite being one of the simplest data structures, it's also one of the most powerful. Understanding how stacks work help you reason about recursion, undo systems, and even how programming languages manage memory. Stacks are essential for LeetCode because many problems require last in, first out, or LIFO logic to track elements, manage nesting, or reverse order efficiently. We can use it to validate parentheses, find next greater elements, evaluate expressions, perform iterative tree traversals, and design efficient data structures. Mastering stacks can help you solve problems involving order, nesting, and dependency, which are patterns that appear frequently in real-world algorithms and interviews. Let's explore what stacks are, how to implement them in Python, and where they're used in real life. As I said, a stack is a collection that follows the last in or LIFO principle. The idea is pretty simple. The last item you place on the stack is the first one that comes off, like a stack of plates at a buffet. If you've ever pressed undo multiple times in a document editor like Google Docs, you've interacted with the stack. Each action is pushed onto the stack, and undo simply pops the latest one off. This is what a stack looks like conceptually. We have the top of the stack, and we have a bottom of a stack. There's a simple list-like structure that you can append to or pop off of. Say we pushed D onto the stack. It would go on top, and then if we popped an item, D would be the first one to go. Python doesn't have a dedicated stack class in its standard library, but the built-in list type works perfectly fine for the job. The two main operations are append, for pushing an item, and pop, for removing one. So looking at this code here, we'll append A, B, and C to the stack. At this point, our stack looks something like this. Our stack looks like a simple list containing A, B, and C. Say we wanted to pop the stack off now. The last item that we added, which was C, would be popped off. When we pop off C, our pop function will return C, will return the item that was popped, and now our data structure only has A and B. Our approach here is simple and effective for most tasks, although list performance can degrade slightly with very large stacks, since lists are optimized for random access and not necessarily stack operations. For heavier or performance-sensitive workloads, Python provides a DEque from the collections module. A DEque, or a double-ended queue, is built for fast appends and pops from both ends, which gives us true O of 1 performance for stack operations. This example is very similar to our example from above. Say we appended task 1, task 2, and task 3 to the DEque. For each pop call, we would expect the reverse order in which the tasks are popped off. So our first pop should return task 3, and our second pop should return task 2. And if we theoretically wanted to pop again, we would get task 1, and then we would just have an empty stack. And we can see that this works as expected. The DEque is ideal when you need both speed and flexibility. You can easily reverse data, simulate browser navigation, or manage undo actions without worrying about performance overhead. You'll often need to check what's currently on top of the stack without removing it. So we can use the peek function by accessing the last element with stack index of -1. Say we had a stack that looked something like this with login, dashboard, and settings. And let's say that we wanted the current page. This code right here should give us settings. It's also important to handle empty stacks gracefully. Calling pop on an empty structure can raise an index error, so it's good practice to check before you remove an item. Stacks appear in more places than you might think. They power many of the systems that you use every day, like undo, redo systems. Each action, like typing or deleting, gets pushed onto a stack. Undo pops the last action, and redo pushes it on another. We can also use it for browser navigation. For example, every time you visit a page, it's added to a stack. Clicking back pops the current page off. We can also use it for expression evaluation. Compilers and interpreters use stacks to process operators and operands. We can also use it for function calls. When Python runs a function, it stores the state on the call stack. That's why deep recursion can cause a stack overflow. Once you start noticing it, you'll realize that stacks are pretty much everywhere. Here's a simple and classic use for stacks, in that validating that parentheses and expression are properly balanced. This is our implementation, and it is our function to check if parentheses, brackets, and braces are balanced in an expression. First, we'll initialize an empty stack. Then we'll define a dictionary mapping the closing symbols, so we can see that each bracket has a corresponding bracket. Then our implementation iterates over every character in the expression. If the character is an opening symbol, we can push it onto the stack. And we append it to the stack right here. If the character is a closing symbol, then we go on to another check right here. If the stack is empty, meaning no matching opening symbol, or the top of the stack does not match the corresponding opening symbol, we return false. If a matching pair is found, we pop the top element from the stack. After processing all characters, if the stack is empty, all symbols were balanced. If it's not empty, then that means there are unmatched opening symbols remaining. We have a couple of test cases right here. We can see that this is balanced, as in each bracket has a corresponding bracket. And we have a false case, as in these parentheses do not match, as we have mismatched brackets. Let's test it out. Let's take it one step further and wrap all of this logic into a custom class. This makes the stack reusable, clean, and easy to understand in larger projects. Our implementation in Python is a simple stack class with a constructor to initialize an empty list to store stack items. We implement the push method, which adds an item to the top of the stack. We add a pop method, removes and returns that top item of the stack. So you can see right here that is exactly what we're doing. We have a line to check for empty stacks. We'll also implement a peek method, which returns the top item of the stack without removing it. We also, for the same reason, we're going to add the index error as well. We'll also implement an isEmpty method, which checks whether the stack has no elements. We can also implement a size method, which returns the number of items currently in the stack. This is an example usage of our stack class. Say we wanted to push 10, 20, and 30. If we peeked at the stack, we would expect 30. If we popped the stack, we would also expect 30, since peek doesn't remove anything. If we didn't have the pop call here, we would expect stack.size to return 3, but since we just popped off an element, that being 30, we would expect size of 2, that containing 10 and 20. Let's check it out. And that's exactly what we get. Stacks are one of those tools you'll use without even realizing it. When you write code that manages order, memory, or state, chances are you're relying on a stack somewhere under the hood. Learning stacks is foundational for you as a software engineer. It gives you a foundation for understanding queues, trees, graphs, and even algorithms like depth-first search. Once you're comfortable with this concept, everything else in data structures starts to make a lot more sense. And that's the end of the video. Thanks for watching. Leave a like if you found this video helpful. And yeah, I'll see you in the next video.